using different methods which are available. My talk has been made easier by the previous presenters. What they have talked of is from their experience. I will be giving you the basis of whatever was talked upon. So far as financial disclosures are concerned, I am the author of this book, which is in print, which covers everything that any medical practitioner is going to use through the length and breadth of his career, including all the statistical tests, including index numbers, including statistical quality control. We've already talked of the research process. Now the research process is, all research effort is to get to some truth in the universe, to find out some truth about the population. What we are trying to do is, we have a research question, we look at the population, we make some measurements about the various properties of every element in that population, and from those measurements we do some tests, we prove or disprove our hypothesis, and therefore we come to find the truth in our study. So that is the basic research process. All of us do that. Now let me start with an example. For example, you look at the patients in your OPD. So you have, say 50 patients coming to you or 100 patients coming to you. Let's say Ram Singh, 50 years of age, male, adult, say 50 kilograms in weight, 150 centimeters. So Ram Singh is an entity. He is an element in your population. And his gender, male or female, is a variable now. What kind of a variable is it? Out of these ones, it's a nominal variable. It's just dividing him into groups. We've already talked of what ordinal variables are. They follow a particular order, mild, moderate, severe. Now, we talked of other quantitative variables. For example, age is there. That's a quantitative variable. His height, 150 centimeters. 150 times that 1 centimeter, which is a reference which is kept somewhere by the IUPAC. Now what is a discrete variable? A discrete variable is one which can take only integer values. You can have only one death, you can have one birth, you can have one pregnancy, you cannot have half a pregnancy. Therefore that is a what variable? Discrete variable. Now so far as continuous variables are concerned, these are variables which can assume values in between those integers. You can be 41.5 kilograms, 41.75 kilograms. So those are continuous values. Now all this is important because this influences the tests that we have already discussed when we were talking of testing our hypothesis. Now what you've done is you had 50 patients. You have measured the properties of those 50 patients. And now say for age itself, you have 50 numbers. You put it in an Excel sheet and you try conveying that to your reader. Is it possible? 50, 24, 26, 38, 49? It makes no sense. That's raw data. You want one value which conveys to your reader the essence of all that is there in your array of numbers, in that entire list in your master chart. So what do? You pick up one value. It could be an average. You could total all of them, divide it by the number of observations you've got. That is what do you call? What do you call it? Mean or average. You remember Sholay? There was this jailer, आधे इधर जाओ, आधे उधर जाओ, बाकी मेरे पीछे आ जाओ. What you could do is, you could arrange all these values that you have in ascending or in descending order and then pick up the most central value. That would be the median. आधे इधर, बाकी मेरे पीछे. So that's the median. Or you could go for the most stylish number which is available, one which occurs most repeatedly. That is the mode. And depending on the quality of data that you had, these are the best measures of central tendency that you can use. Now you have picked up the measure of central tendency. You have conveyed that the mean is this. but it does not convey the scatteredness of your data. You know, your values could be scattered from 30 to 50, or they could be scattered from 4 till 80. How do you convey the scatteredness is by using one of these measures of dispersion, which could be any of the deviations. Most common one we use is range, the interquartile range, and all of us use this standard deviation. Now, I won't go into the details of how we calculate it, but suffice it to say that standard deviation actually gives us the heterogeneity of the data. It tells us how heterogeneous or homogeneous the data is. If your standard deviation is low, then your data is homogeneous. If your standard deviation is more, then it is heterogeneous and it will require a larger sample size, right? We've already talked of what a normal distribution is like. Then we have other distributions, Poissons, we have binomial, and so on and so forth. Simply spoken, a normal distribution is the bell-shaped curve where the mean, the median, and the mode, all of them have the same value. And how do you find that out? You pick up your data, fire up your statistical software, and run something called the histogram function. When you run the histogram function, you get something like this. Some of the softwares will allow you something called fit to histogram curve. That will just run a curve here and let you see visibly whether or not your data is following a normal distribution or not. Suppose it is an iffy situation, then you can do even more rigorous testing, that is called goodness of fit tests. Now, knowing whether or not your data is following a normal distribution is important because you need to apply the appropriate statistical tests when you do your hypothesis testing. But while on this, when you look at the data, when you are reading a paper, always look at something called skewness. This is what a normal curve is, but it is entirely possible that most of your values are on this side of the mean, in which case it is positively skewed, or they are on this side of the mean, in which case it is negatively skewed. So if you see something like this, don't get scared. It is just telling you whether it is, something like this, or the values are skewed on either side of the mean. Another thing that you will also come across when you're looking at the printout from your statistical software is something called kurtosis. Kurtosis is simply telling you the peakedness of this data. Whether all the values are concentrated right here in the center, in which case we call it leptokurtic, or they are spread out right at the sides here and here, in which case it is platykurtic, flat curve, right? So don't get confused with kurtosis. Now once you have done that, you have described your data to the reader, to the editor, and when you are reading, you know what your data is trying to speak to you, is trying to convey to you. Now you are ready to test your research question, to test your hypothesis. How it is to be framed, why it is to be framed is beyond the scope of the present discussion. So what we do is basically we frame a hypothesis, we assume another hypothesis, and we frame an alternate hypothesis. And after that we carry some tests, we take a p-value, and depending on the p-value we say whether it is statistically significant or not. Is that what we do? All of us? Are we agreed on that? All those who are agreed, please raise your hand. Right? Now let me take you to the basis. Why do we do it like that? This is the reasoning for it. See, when we were doing high school mathematics or geometry, if we had to prove a theorem, we would make a conjecture. For example, if I had to prove that 2 plus 2 is equal to 4, what would I do? I would make a conjecture that, see, let 2 plus 2 not equal to 4. Now I have two sides of the equation, 2 plus 2 on this side and 4 on this side. Then I say, I'm going to carry out a mathematical operation wherein I remove 2 from each side of the equation. So I remove 2 from here. 2 plus 2 minus 2 is 2. And 4 minus 2 is 2. And my equation says 2 is not equal to 2. So my conjecture is absurd. The result I'm getting is absurd. Therefore, my conjecture was wrong. Therefore, 2 plus 2 is equal to 4. Something of that sort is happening when you're testing your null hypothesis. We assume everything to be equal, and if we do not have enough evidence to assume the alternative, then we say everything is equal. The null hypothesis stands. Now, let me explain it in the medical parlance. All of us are familiar with this confusion matrix. Are we? You remember, this used to be A, B, C, D. Test positive, test negative, diagnostic testing. Are we agreed on that? Right. So, the purpose of any test is to pick up all true positives, pick up all true negatives. And we don't want false positives. We don't want false negatives. Our sensitivity used to be true positive as proportion of all positives. Our specificity used to be true negatives as proportion of all negative. Agreed? Now, let me extrapolate it to statistical testing. This is what your statistical test is doing. This is your alpha error. False positives are your alpha error. That is the level of significance that you said. 0.05, 0.01. Right? And your false negative rate is the beta error. This is read into the power of the study. If the power of your study is 0.8, then the beta error is 0.2. 1 minus beta is the power of your study. So basically that is how diagnostic tests operate, and that is how statistical tests also operate. Now we've already talked of correlation coefficient. Can I continue? Alright. Correlation coefficient we've talked of. It simply says how well the two values occur together. This is, the values are between 0 and 1 as Dr. Nayak had already pointed out. This is plus 1, this is minus 1. This is good correlation. If they are scattered all over the place, then it is 0. Why this is important is, when you're looking at continuous data or you're looking at ecological studies, you will use this parameter to calculate your sample sizes. Right? Now why do we want to calculate sample sizes? Why not go ahead and study the whole universe? It has already been answered in parts. There are mainly 3 or 4 main reasons for it. The economic reason is there. Lesser number of people you study, the lesser is the cost. Sometimes when you study the whole population, which is called census inquiry, by the time you get the results, the primary situation has already changed. So it becomes irrelevant, right? That's the time domain to it. Then of course is the scientific reason. If you do a study which does not have adequate power, then what you are doing is you're coming to a result which has no validation. Right? It does not prove what you're trying to prove. It could be due to a chance error. And then of course you have ethical reasons for calculating your sample sizes correctly. And the ethical reason is, whenever you do study, you are exposing your patients to some sort of harm. And if there is no commensurate benefit, then there is no point in exposing your patients to harm. Therefore, if you have an underpowered study, lesser sample sizes, you are actually doing an unethical study. Why do you need to, we talked of the variation, the variability. We have these biological variabilities, and looking at those variability, we calculate our sample sizes. After calculating it, you also make some adjustments for potential dropouts. I need to study 100, but I feel 20 are going to drop out. So I will be taking 120, out of which I believe 20 will drop out. Dropouts may be more, right? But that is again a judgment that is there, or sometimes we try to calculate it backwards. Now there are this particular question of sample size estimation, ideally the ideal one is the a priori approach. This is the question I'm studying. This is the clinical effect that I desire to study. Therefore, this is for this given power, this significance, this is the sample size I need to have. This is the best approach. But many times what is going to happen is, you are sitting in a clinic, you have data lying in front of you and you need to take a decision on it. Now we come to something called the bounded rationality approach. The bounded rationality approach, here what you can do is, you can punch in all those values into your software and realize that for a given alpha, what is the power of your study. So when you take a decision based on that, you know that, it is more scientific. It is not 100% proven, but within the realm of this, your judgment is supported by mathematical analysis, by scientific basis. Try to get to 0.8, but even if it is a little less, you have at least some grounds for having made that decision. Now when you want to calculate your sample sizes, the easiest method is fire up your statistical software. What I use is Stata, and this is what you're going to get. Go to statistics in Stata, come down to this which says power and sample size. When you hit this one, you will get something like this. Here you give the mean, the standard deviation, hit OK, and it will tell you what is the number of patients you would be requiring. Now this is different in case you have paired observations. It says test of mean in repeated measures. This is for paired observations. So paired observations, if you choose this one, you will get this kind of a dialog box. Again, you put the values and you hit OK and you get your sample size. There are other softwares which are available. Procedure is almost the same. It may be in another menu. In Stata, there's something called SAMPSI. That's the code you run. You type SAMPSI and then you put your values, you get that from Stata directly. You also have online calculators and web resources which are available to you. In the unlikely event of not having access to the internet, we can go back to the good old way of using the formulae and using the nomograms. I'll just briefly cover the nomograms because very commonly we use it. So all of us have done that. Hypothesis, you've already framed, you've done your alpha and beta, and now you want to go ahead and find out you've given an effect size and you want to calculate your sample size. There are different formulae which are available. You have to decide which type of test of significance will be used, one-sided or two-sided. And then you have different type of studies, descriptive studies and analytical studies. In descriptive studies, the sample sizes will be a little larger. In analytical, they'll be a little smaller. Now, let me give you an example here. It's a continuous variable, a descriptive study for medical students. Now, this is the width of your confidence interval, which is plus minus 3. So, what is the width? 6. Standard deviation that you got from the previous study was 10. So, this particular value, W upon S, comes as 0.6. You go to the nomogram, go to 99% confidence interval, go to W upon S of 0.6, and what do you want? A sample size of 74. Similarly, you can do it for dichotomous variables. Pick it up, width, confidence interval, this is your width, this is your expected proportion. So this is your alpha, this is your beta, and you get your sample size here. And so on and so forth. There are n number of nomograms which are available. They are available online and otherwise. Just a word of caution when you're using correlation coefficients. When you're using correlation coefficients, you'll often come across the situation where it will say it is minus something. In that case, what you need to do is, you need to use the modulus or the absolute value of that R. For example, it says R was minus 0.3. There is no nomogram which will give you minus 0.3. So you need to use 0.3 and go to your 0.3, go to your level of significance of 0.05, look at beta of 0.2, that is 80% power of study, and this value, the sample size is 85. So there are different variations on the theme, but broadly this is how you will be calculating. I think with that I will end my talk, and I request all of you to kindly give a feedback to the AIOS on how you found this particular instruction course.
2 hours.
Yeah.